Sean, please. Sean, please, you can't see anything, or have you started, or?
Oh, sorry, I've just come. Let me start presenting. Can you see?
Yes.
Okay, fine. Me and Elizabeth were doing question 4, so I'm going to do 4A and D. Yeah, so question 4A starts with the help of a clocked JK flip-flop and waveforms, explain the working of a 3-bit binary ripple counter. So a ripple counter is asynchronous, so the clocks for each of the flip-flops don't they won't come from the same source. So that's basically how the this ripple counter work. The clock from this first flip-flop, this second flip-flop will get its clock signal from the output of this first flip-flop. Then it goes on like this. And yeah, so this is basically how the timing waveforms will come out. Because of this inverse in the clock, yeah, the waveform, the flip-flop will be triggered by the falling edge of the clock. So this first flip-flop will be triggered by this falling edge. So it will change from a 0 to a 1, gets triggered again by the falling edge of this clock. Then now it will go flat again. Then as the second flip-flop, which is now getting triggered by Q0, will be triggered by the falling edge of the output from Q0. So that's when it will come up. That's how it gets that's how Q1 will be able to be changing from 0 to 1 at a different rate from Q0. And that's how now the same process will go on for also Q2, where it's getting triggered by the falling edge of Q1. So it will come up when Q1 is coming down. So yeah, I've just explained the operation. Then from the truth table, you can see basically Q0 will at the first clock signal point here, Q0, Q1, and Q2 are at 0. But at the first point, to have 0, 0, 1, it's only Q0 that has changed from 0 to 1. Then at the second clock signal point, you can see that it will be only Q0 will change back to 0 because of the falling edge of this clock signal. But now Q1 will be triggered to come on. So that's how it goes from 0, 0, 0, 0, 0, 1, then 0, 1, 0. Then the same process will go on to become 0, 1, 1, then 1, 0, 0. So that answers question 4A. Then for 4D, how many RAM chips are required to provide a memory capacity of?
Could you show the picture of the arrangement of the flip-flops?
Okay, let me go up. Here.
Also, the inputs of J and K are both at 1.
Yeah. So for JK flip-flop, when J and K are at 1, the new Q value will be the inverse of the old Q value. That's how it keeps on changing 0, 1, 0, 1, 0, 1.
I think.
Yeah. So to 4D1. So the total memory capacity that's needed is 2048 bytes. which is when you change it to bits, it will be this amount. Then the capacity of each RAM chip will be 128 times 8, we get this. So therefore, the number of RAM chips, it's basic division, you'll get this. Then for part 2, how many lines of address bus must be used to access 2048 bytes of memory? Now, I wasn't sure of how to do this part because it seemed too straightforward to just, go from, since it has 128 memory allocations, you just do log 128 divided by log 2 to get 7. It seemed too straightforward for what, Prof. Mwangi is used to, but I just left it like that. But if anyone else can see, like if there's another way to do part D2, that would be helpful. Then part 3, how many bits must be decoded for a chip select? Now, I was assuming since now we have 16 RAM chips, I was assuming that we'd need a binary decoder for this like computer or whatever that's using all these RAM chips to be able to decide which RAM chip will be used at each point in time. So from the 16 output lines, I just did log of 16 divided by log of 2. We get the 4 lines that will be needed by that binary decoder to determine which RAM chip will be running. So that's how I got that 4 bits needs to be decoded for chip select. Then the size of the decoder, I just straight away said that it's going to be a 4x16 bin deck. So I'm done with 4A and D. So now it's up to Elizabeth to do B and C.
Hi.
Hi. Elizabeth, you're muted.
You can't hear me?
Nigel, could you please not present because Liz is having some technical issues she's trying to fix. Nigel.
Okay. So nianze tu sio?
Yes.
Okay, sawa. Let me present my screen basi. You can see my screen?
Yes.
Oh, okay. Question 3. Question 3C. Given a 64 by 8 ROM chip with an enable input, show the necessary external connections needed to construct a 256 by 8 ROM using an appropriate number of chips and a decoder. Okay, let me go to where I wrote it. So we're given a 64 by 8 ROM chip. The 8 here, as you all know, represents the data. The data is 8-bit, and it's stored in 64 locations, the addresses, or it's stored in the ROM. So in order to get the input into the ROM, we all know that a ROM has a decoder inside, which gives the input of data inside the ROM. So kupata input ya ROM ya decoder, unafanya 2 power n is equals to 64. This is 64 now. Now the n will give you the number of inputs, which is now 6. So I drew my ROM over here, 64 by 8 ROM. The decoder is inside here now. Its output 8-bit data, then the input is 6-bit, and it has an enable input hapa tumeambiwa. Okay, so moving on, showing the necessary connections, external connections needed to construct a 256 by 8 ROM. Now, if a ROM chip yenye tumepewa 64 by 8 ROM chip stores 8-bit data in 64 locations. Now, what about here yenye tumepewa 256 by 8 ROM, where it stores 8-bit data into 56 locations. So in order to get the number of chips, you divide 256 by 64 to get the number of chips now. You divide here unapata 4. So this gives the number of chips. So we're supposed to use 4 ROM chips. So I went on and drew the external structure of it. I took this ROM now, because there are 4 of them now, and this is just the upside down. There are 4 of them, each with a chip enable inputs, and their input. Ignore hizi vitu zingine kwanza. Let's just focus on these 4 ROM chips now. All of them have 4 enable inputs and 6-bit data input. Remember that they all have decoders inside them where a data inaingia, and an output of 8-bit. Yeah. So in order for us to get in order for us to get to select the number of chips that we are using, because we are to design a 256 by 8 ROM, so the output is supposed to be 8, but now we have all our 4 ROMs, and they all have an 8-bit data output. So we need to select one of them will be giving us the data output. So in order to select one of the 64 by 8 ROM chips, we need a decoder, another decoder now. So because they are now the chip and the decoder, the output of the decoder will be going to the inputs enable of the ROM chips now in order to select which ROM to use. So there are 4 ROM chips. Now that's the output of the decoder. 2 power n is equals to 4, just like here, just like upper. So in order to get the number of inputs n, it's 2. So I drew a 2 by 4 decoder with 2 inputs. Ignore this I6, I7 kwanza. And now the output of the decoder is going to each of the input enable of each ROM now. Now I chose the third one to go to this one, second one here, first one here, and this one, no, okay. This is the fourth one, third one, second one, first one. Okay, this is supposed to be a straight line. And then the 2 inputs now, if it's 0, 0 now, it will select the first one. So it will select this fourth ROM. If it is 0, 1, this ROM, 1, 0, this one, and 1, 1, it will select this one. Then we're remaining with these inputs, ROM inputs, which have what? N inputs. So I took these N inputs, I connected it to one line, to how can I say it? I made a common bit line from I0 to I5 for the 4 ROMs now. That will be I0, I1, I2, I3, I4, I5. Now, depending on which ROM we are supposed to use, it will dependent on I6 and I7. Now, after you select the ROM you're supposed to use, now the last 2 bits are to decide which ROM we are supposed to use. And to fourth are supposed to select the data input into the ROM that we're supposed to use now. So for the 6-bit input, it's common here. So I connected this one, the input of this ROM, the input of this ROM, this ROM. Then I made them to have a common point over here. But the ROM that we're supposed to use is dependent on this decoder now. And then the output of each ROM, since we're supposed to have an 8-bit data out, all of them have 8 bits. I connected it to just all of them to one line so that whenever we select one ROM from I6 and I7, it will give us the ROM that we're supposed to use, and that ROM that we're supposed to use will give the number of bits, the data out. So we can confirm this is what you're supposed to draw. We can confirm it using the number of inputs, because from I0 to I5, that's 6 inputs. Then I6 and I7, that's 7 and 8. So our entire ROM chip, our entire ROM, 256 by 8 ROM, composed of 4 64 by 8 ROM chips. Composed of 64 by 8 ROM chips, have 8 input lines. So in order to get the number of input lines, just generally, in Ahonga 2 power n is equals to 256. 2 power n, which gives 56, the number of n, the value of n, sorry, gives 8. And from our diagram upper, took on 8 pins. So yeah, that's how I went about that question. Kama kuna mtu ako na swali about it, tafadhali uliza. Any question? Oh, okay, tuendelee, sindio? Question D. Describe CMOS inverter and state advantages of CMOS. So CMOS, it's a combination of both NMOS and PMOS. The C just means complementary metal oxide semiconductor. It's a combination of NMOS and PMOS. So now PMOS initially, okay, it has a faster switching speed than compared to NMOS. So I put an arrow over here. But it has a large fabrication density compared to NMOS. So in order to make good of the two, they had to combine them to give CMOS. And also another fact about them is their dualities of one another, duality ACT. Now to the inverter, this is how it looks like. I described it by drawing it. The VDD, the gate, it's composed of a PMOS and an NMOS. PMOS, it's always on top of the NMOS if you're drawing the inverter, always. So the gate of both the PMOS and the NMOS, they're connected to give a single input, and then the output Y is connected over here. So on to its description. Say we have a high over here, 5 volts. If we input 5 volts over here, it would be 5 here, 5 here. But now, this 5 illustrates that, and also a PMOS, it's always illustrated with a blob over here. This is how kuweka a blob. So when you connect 5 volts over here, it reads 5 upper, now 5 upper, it's a high, okay? And then the NMOS is on, but remember, since NMOS is a duality of PMOS, if NMOS is on, the PMOS is off. So this output Y, it can't get voltage from over poleni. There's some dogs fighting, so you come nasikia, poleni for the noise. I lost my train of thought. Okay. A high over here, get 5, get 5. This is on, this is off. The dualities of one another. Now, why the output will be pulled to the ground because it's not connected up, and because this is on, to pull to the ground. So when we have a high, it gives us 0 volts because it's pulled to the ground. And now, when you have a low here, explained in this other diagram, from A, it gives 0 volts, 0 volts. 0 volts determines the state of the NMOS now. The NMOS will be off, and since the NMOS is off, the PMOS will be on because the duality is here. And then it's connected to the VDD. So when we have a low input, it gives 5 volts as the output. The Y is pulled up now. It's not connected to the ground. It's connected to the VDD. It's pulled up. Yeah. So that's the description of it. Advantages of CMOS. Its advantages, it has a high, its power dissipation is at the gate is low. It's nearly 0 because most transistors draw very little current from the power supply. That's one. 2, it has a high fabrication density and is therefore used in VLSI devices. VLSI just means very large scale integration, such as microprocessors and memory chips. And then the 4th one, it has a high noise immunity. And the 3rd one, sorry, it has a high noise immunity. And then the 4th one, it has a high input impedance. So I got all these 4 advantages. And something interesting about this advantage, for the gamers out there, or for those who follow the war between Intel and AMD, recently, Sijuka may notice Chief Engineering Officer wa Intel alifutwa kazi, okay, hakufutwa kazi, aliresign, but in this case, it's the same. Reason being stocks AMD zilipita Intel for the first time, though Intel it's still bigger than AMD. And reason for the stocks surpassing that of Intel is that AMD found a way to create their microprocessors and their graphic processing units in their central processing units and their GPUs into one APU, and it is as small as 7 nanometers and 5 nanometers. But now Intel is still stuck on 14 nanometers. They promised to deliver 7 nanometer before AMD, but AMD delivered the 7 nanometer whatever core mbele yao, and in that 7 nanometer accelerator processing unit, it uses Cmos. So they found a way to make Cmos very small. So I think that's an advantage. Yeah. So kama kuna mtu ako na swali aniuliza, that's the end of my presentation. Okay. I thought high fabrication density was a major weakness of Cmos. Could I get clarification here? No. I think no. It's not a major weakness. It's an advantage actually. Iko kwa book yake. As an advantage of Cmos, sijui kama kuna kitabu yake, wacha nitafuta. Just a minute. A minute. See hapo. Sema siko wapi Cmos.
Page 97.
297.
97.
Oh, 97.
But I think to answer her, high fabrication density means like you can pack on more transistors or more MOSFETs
on one
within a certain area. So in terms of making computer chips and microprocessors, that's an advantage.
Yeah. Cmos has a very high fabrication density.
Hello.
Guys, for question 4, I think they can continue.
Please.
Okay. Okay. Am I audible?
Yes.
Yes.
Okay. So Can you see my screen? Okay. Mhm. Okay, so I was doing question 4B and 4C. Okay. So 4B, differentiate between static RAM and dynamic RAM. And then draw the circuits of each cell in MOS technology. Okay, so SRAM comes both in bipolar and MOS technology. Okay. So yeah, starting with the B, like a brief differentiation is that the basic cell of SRAM is good over MOS or bipolar flip-flop with facilities for writing, storing, and reading data, whereas the basic cell of a DRAM is comprised of a capacitive circuit and a single MOS transistor. And then I didn't write because the basic explanation of the working of either cells is clearly explained in the notes. I felt like I was repeating myself, so I just opted to present and explain using the textbook. So, like the basic MOS cell, or the basic MOS static RAM cell is illustrated here. So it has like 6 transistors, of which T1, T2, T3, and T4 comprise a flip-flop. And then T5 and T6 basically make up, they control like the reading and writing operation, okay? Yeah. Wait, am I still audible? Fiona, can you please confirm if you can, everyone can hear me?
Yes, I can. I can hear you, please.
And I'm seeing guys saying they can't see.
Oh yeah, I can only see a
the
blank page.
presentation. Any
The
page 234. Of the need text. I'm using the textbook as a reference. But I don't know. Like maybe the Wi-Fi is slow. Okay, so does everyone have access to the textbook? Because like the presentation will not go through. Okay, let me just finish up what we. Okay, so T7 to T10 control the read and write operations, and are not really an integral part of single. Like T7 to T10 is shared by multiple cells. Yes. And then the circuit T1 to T4 being the flip-flop has 2 stable states. When T1 is on and T2 is off, a logic 0 is stored within the cell. And when T1 is off and T2 is on, a logic 1 is stored. Yeah. So that's like the basic working of the cells. There's more detail in the textbook, but to answer the question, I think that explanation suffices. And then moving on to the DRAM. Okay, so the DRAM only exists in MOS technology, comprising of a capacitive circuit and a single MOS transistor. So this gives it a very high fabrication density. Yeah. Because it uses a single transistor as opposed to the SRAM, which is using 6.
Is Elizabeth still presenting? Fiona? Fiona, is she?
Yes. Sorry. Yes. Yes, you said.
Is Elizabeth still presenting?
I don't know what has happened. I think I mine was a little bit when she was presenting and something about the textbook. That's the last thing I got.
Okay. See, if there was someone else meant to take after Sieneza, shughulikia while tuangalie kwani what's if she can get back online. Wait. Oh, that is there someone else meant to do it with her?
It will Sean clarify for us. Sean, we are a bit lost. Are you guys like done? Is that the last one?
Yeah, she was meant to finish up, but I don't know now what happened with the internet.
So okay, so what we can do now, okay, I'm seeing she's, okay, she's presenting. Let's just give her time. Okay, I think she's gone. Okay, let's just give her like up to 9:50. We can all be looking at the link which Kishiro sent. But is it typical? I'm trying to check if the one I have in the book, if it's clear, but we can all be looking at the link which Kishiro sent down for ACT in the meantime. Kishiro, could you send it again? It's right. The ones who just joined can see it.
Fiona, Elizabeth has said her Wi-Fi is like really bad now that she won't be able to finish her presentation.
Oh, okay. Can you finish it for her? Were you guys doing all of those questions together? Or you did that question?
No, we had split up the work, but let me see.
Okay, in the meantime, the print on the okay, so the link, it's not very clear, but it's manageable. The one I have here, the hard copy it's better. I can say it's better than that. At least you can see some equations, but not all. But I think some of these things, it's only the useful information part which is not very clear. So I think we can use it. I mean, the useful information part we can get it from the internet, like things like those equations that you don't butcher the spelling, so the pronunciation. So those ones you can get them from the internet. Those are the useful information part. But other than that, these other parts, the questions that are clear. Okay, Sean, have you looked at this?
I'm looking through it, and I think I can maybe answer part B, but that's what she had already done when she was presenting.
Mm-hmm.
I don't know about C.
Oh. Mm-hmm. Okay, it's okay, Sean. I don't want to give you so much pressure to do it, but maybe we can give her time. I think the next time she can present. Now we can just. Okay, guys, I know most of you have been asking about the online exams and if they're coming or not. The last time we spoke to some guys who are in the administration. Apparently, our chairman is very ready to give us the exams. So I think we should just ride on that and just be very much ready. And as much as schools are going to be opened officially in 2021, I think the thing also said that online exams and something to do with e-learning must go on. And I also have a feeling like our lecturers can't. I think also, going like for a whole 3 months without doing anything is something I think our lecturers cannot handle. Also, because the whole thing of get paid and all. Because okay, my thinking is that the exams will still happen very soon. So I still think we should continue the discussions. So okay, first we can choose which questions for ICT, then we can choose which days of the week we'd like to meet. So I don't know. Someone was trying to. So you'll just bump with me, guys, right now. Okay. So, do you guys want me to present my screen so that you can all see the ECT paper, or can you all access the paper? Maybe 2 people can answer.
Just
Sorry?
You can present.
Okay. Sorry, guys, you just bear with me. I have some things which are moving. So Okay. So we have those. That was the useful information I was talking to you about. So that those are things you can get from his book or the internet. Yes. Can you guys see my screen?
Yes.
Okay. So there's question 1. Question 1 talks about things to do. It's basically chapter 1. For those who can know what chapter 1 is all about. Open circuit impedance, definition, Z parameters, Y parameters, all that. That's for question 1. Question 2, what is this? Question 3 is about what? Transmission lines. That should be a good one for anyone. Question 3 is about also transmission lines and something to do with stub. Okay, question is that what is this I keep doing? Yeah. Then question 3 is that VSWR. What did that mean? Something ratio. Then there's question 4, something to do with band pass. I will scan my paper and send it to you guys so that you can see that question 4 part nicely for anyone who wants to choose. But if you want to choose that, it has something to do with filters, something compare prototype and M-derived passive filter circuits, design a constant K low pass T and pi section filters, even the cutoff frequency is something. So yeah, so it's question 4 is about filters. Yeah, so we have that. Yeah, so maybe you guys could start choosing. Okay, so no. Okay, we will go one by one. Question 1. Z parameters, Y parameters. It should be very simple. Guys, come on, this is ECT, man. Question 1. Okay, can anyone
Check
hear
your
me?
chat. Kuna watu wanajibu huko.
Wapi?
Kwa chat.
Oh my God, really? People have chosen.
We've started.
Oh, okay. Okay, good, Nigel, good, Danson. Does anyone want to join in that group? We just need one more person there. Okay. Great.
Peter,
Question 2. Okay, very good. Question 1 is gone. Let me write this down. I'll write. Question 2. Question 2 has something to do stub matching, quarter wave transformer, load impedance and input impedance, uniform transmission lines, characteristic impedance over distortion loss. Okay, this one looks very interesting. I don't think I know any of this. Anyone? Anyone? Okay. Anyone? Nasikia mtu anapata notification. Afanye tu. Some people are texting each other. Guys, come on. Okay, let's skip number 3. Okay, question 3. Question 3 has, for those who are not attending, who are not, it's transmission lines actually. I think this one will have to use the Smith chart. I don't know. No, I don't. Yes, you have to use a Smith chart. Good, Lynn, for question 2. Question 3, Surya Smith chart. It's your time to put your mind to the test. Okay, what will come on now? Okay, very good. Okay, acha niandike yangu. Question 4 is mine. Okay, very good. Who will join Lynn in question 2? Come on, guys, let's welcome Lynn to the presenting mood. Come on, guys. I think at this point I have to cheerlead you guys to do questions. I think it's for your own benefit also. Very good, Kamara, very good. That's nice. So far, question 2 only has 2 people, and question 4 only has 2 people. Are you guys okay like that? Do you need one more person, Lynn and Kamara? Okay. I guess that's it. If no one else is willing to add their name to another question. Okay, very good. So now I think we'll go to the next agenda. I don't want to keep you guys waiting because it's already, I want us to be done in 5 minutes. Okay. Okay, first order of business, Joseph, please add Alvin to the WhatsApp group. Second order of business, which 2 days are we meeting in next week? We decided 2 days so that we can all have time to go through the previous papers. So what we'll do, I will just only allow 2 people to talk. Which 2 days they want, then we vote. Okay, let's say 3. Let's say 3. Okay, someone to just give the 2 days and just go right now. We don't have a lot of time. Okay, yes?
Before you continue, I was looking up Liz's question, the question 3, and I think I can explain for people if you all want to.
Yes, definitely.
So, ROM is read-only memory. I think all of you know that. And then the first category, according to my notes, was a masked ROM. And that one, the data within it is written while in fabrication of the ROM itself, so in the factory. Then you have programmable ROM, which can be programmed even after fabrication. So in the field or for whatever use you're going to use it, you can program it there. Then Eprom is erasable programmable ROM. Different with the prom, this one you can clear whatever you had written to the ROM, and you can write something new to it. And then the final one, Eeprom, is electrical erasable programmable ROM. And that one, the code you put into the ROM can be written while the ROM itself is within your working circuit. So for the prom and Eeprom, you have to remove it from your circuit, and then you can write, and Eeprom you can erase and write. Eeprom you can write it while it's still within your circuit. Yeah, I think that's basically it.
Thank you. Thank you, Travis. Thank you so much. Oh God, I've just realized I've been recording this whole time even I'm not choosing, but yeah, thank you. Now it's recorded. Now I don't think Liz will have to continue from that. Thank you so much, Travis, for looking at it. So now I'm going to stop recording.